Assalamualaikum and good evening. My name is Ahmad Syalimin bin Muhammad Amin. Today I will present for the IoT mini project, which is a IoT based smart tunnel monitoring system. For the background of our project, which is a tunnel in urban area are vulnerable to flooding and hazardous condition during a heavy rainfall. Sudden water rise in tunnel can cause accident and also vehicle damage and traffic disruption. So conventional tunnel monitoring system often rely on manual observation and also delay a response. For the problem statement, tunnel condition can change rapidly due to the rainfall and also rising water level. Manual monitoring may not respond fast enough for the during emergency situation, and also sometimes vehicle may still enter a tunnel during unsafe condition, and it will increasing the accident risk. So the objective for our project, which is to monitor tunnel environmental during condition using multiple sensor, and also to determine safe or dangerous situation based on the predefined threshold, and to control a servo motor acting as a automatic tunnel gate, which is for the hardware and sensor integration. For the component that I use inside our project, which is first one is ultrasonic sensor. It used for measure water level at the dam, and the second one is water level sensor. It for the detect water level inside the tunnel. The third one is rain sensor. Rain sensor is to detect whether the raining heavily outside the tunnel. And for the microcontroller, we use ESP32. It read all the sensor and decide if the tunnel is safe or dangerous. And for the red and green LED, we use as indicator. And lastly, for the servo motor, act as a actuator for the tunnel gate. This is a circuit diagram for our project. This is a flow process of our project. This is a block diagram for our project. You can see from the sensing layer, it go to the internet layer, and it go to the internet, and then it go to the ESP32 to make a division, and it will send data to the dashboard and also to the Telegram alert. This is a problem faced during the process of the project. The first one is sensor reading fluctuated and not consistent during operation. So for the solution, we use V-in for the ultrasonic sensor and 3V3 for the other sensor. The second problem, which is analog sensor value are affected by noise and causing unstable analog to digital reading. So for the solution, we reduce wire length between sensor and ESP32. That's all from me. Thank you.
I'm student B. My name is Muhammad Shafwan bin Anis, metric number 231061512. So this is the IoT architecture full overall for overall system, which consists of prospection layer, network layer, middleware layer, and also the application layer. So let's go one by one. So for the prospection layer, the sensor utilized is ultrasonic sensor, water level, rain sensor to gather data on the river distance, flood level, and rain intensity. The processing is using the ESP32 microcontroller to process the data, trigger action like visual alerts using LEDs, and control physical gates with servo motor. The next is the network layer. The connectivity is Wi-Fi via the ESP32 transmit data, and the protocol used is the MQTT protocol to handle data communication effectively and efficiently, and the broker used is the HiveMQ communication, cloud routes data for real-time monitoring. The next layer is the middleware layer. So its processing is the Python bridge to evaluate the sensor data and apply safety logic, and the storage is we use the InfluxDB for fast retrieval and analysis, and for the alerting we use the Telegram bot API to send alert for critical event occurs. And the last layer is the application layer. With visualization, the Grafana, we use the Grafana dashboard to display real-time data with visual alerts for the operator, and for the alert system we use the push notification via Telegram for the critical conditions. And the next is the system analysis and the specification. For the Wi-Fi and hardware, so we use the Wi-Fi IEEE 802.11 BGN for connectivity, offering 150 megabytes transfer rates. And for the ESP32, we use a power-efficient microcontroller with a range of 50 meters indoors and 100 meters outdoors. For the protocol, we use the MQTT protocol, which is lightweight with low overhead but relies on centralized broker, which could be a single point of failure. And Wi-Fi limitation is the power drain is higher compared to alternative like LoRaWAN. And the third is the cloud service. So we use HiveMQ as a message broker, but it's limited to 10 GB bandwidth per month, and the InfluxDB is optimized optimized for time series data with a retention limit of 30 days on the free tier, and for the Grafana here to provide a real-time data visualization for the trend analysis. So lastly is the interface example for in FluxDB and also the Grafana. So the system interface allows us to explore the real-time data series, while Grafana display the real-time status, including the river level and flood rates, helping operator to make a quick decision.
Good day, doctor. My name is Chian. So now is a data analytic part. I'll explain the graph. For the first graph is box plot, water level by month. The box plot show water level distribution are relatively low and stable in early months of the year, indicating mostly safe tunnel condition. In contrast, the later months, especially November and December, display high median and wider variability. These months also show more extreme values, suggesting an increased likelihood of the flood-related condition. This indicates strong seasonal effect in tunnel water level. The second one is also the descriptive graph. It's a line chart. Line chart average water level by month. So it will show the gradual increase in average water level towards the end of the year. Highest average water level occurs during the monsoon period, particularly in November and December. This confirms that tunnel water level followed a seasonal pattern and tend to peak during the period of heavier rainfall. Third one is scatter plot. Scatter plot is also using the rain sensor vs the water level sensor. The scatter plot indicates a clear positive relationship between rainfall and water level. As rainfall intensity increases, water level generally increase as well. However, some points show high rainfall without extreme water level, suggesting that the drainage system is sometimes able to manage rainfall effectively. This highlights that the rainfall is major and not only a factor influencing the flooding. The next one, number 4, is dual axis chart. The dual axis chart shows the peaks in rainfall rainfall and followed by increases in water level over time. In several instances, the rainfall rise first and the water level increase shortly after, indicating a time lag effect. This temporal pattern strengthens the interpretation that rainfall events directly contribute to the tunnel water level rise. And then it indicates the flood event is very low in earlier months of the year, but increase significant during the later month. The highest flood probability is observed in November and December, indicating that these months have the greatest flood risk. This provides predictive view of when the flooding is most likely to occur. Next one, histogram, is about water level distribution. It shows the most water level reading falls in the safe and alert range, indicating that the tunnel operates under normal conditions for the most of the year. However, a smaller but important portion of reading falls into the danger range, representing rare but critical flood events. This right skew distribution highlights that the extreme flooding is infrequent but impactful. Number 7 is the risk level bar chart, and then it shows the safe condition dominate the data set, and the alert condition occurs less frequently, and the danger condition occurs the least. Despite being fewer in number, the danger events are operationally critical as they will represent periods where tunnel safety may be compromised. This emphasizes the importance of focusing on high-impact, low-frequency events. Last one is the risk heat map, and it is risk level by the month. Heat map clearly shows the danger level events concentrate in November and December, while other months are dominated by the safe condition. Alert level events appear more frequently during the transition months. This confirms that flood risk is seasonal and predictable, allow the tunnel operators to prepare for high-risk period in advance. Okay, next slide. The data analytic approach is what I explained just now, or the 8 graph: descriptive, diagnosis, predictive, and prescriptive. And then the key findings is the results show that water level peaks during the monsoon season, particularly in November and December. And then a strong positive correlation was observed between rainfall and water level. In addition, the flood probability exceed 70% during peak months, indicating significant elevated risk periods. For the risk classification logic using the predefined threshold I will show later, the tunnel condition will classify in safe, alert, and danger state. Safe indicate normal operation, alert is triggers the increased monitoring and danger activity, tunnel closure, and pump operation. So the impact for the SDG 11 is enabling the earlier flood warning, improve tunnel safety, and enhancing urban resilience through the data-driven decision making. So the last one is we have the notification in the Telegram. So here is the threshold for each sensor. First one, ultrasonic sensor, the threshold for safe is the reading when greater or equal to 15 cm. And then the alert is 10 to 14 cm. And then the danger is when the ultrasonic sensor sends less than 10 cm. And then for the water level sensor, is the safe one is greater than 600. Alert is 600 until 999. And then danger is greater than 1000 reading. Water level sensor. And then after that is a rain sensor. Rain sensor when dry, safe condition is the value there. And then moderate rain is an alert. And then heavy rain is the danger one, 0 until 2999. So the beside there is a Telegram show when the ultrasonic sensor sends less than 10 cm, it will show the notification, and also for the water level sensor and rain sensor. That's all from me. Thank you.
Assalamualaikum and good evening. My name is Ahmad Syalimin bin Amin. Today I will demo for the mini project for IoT for student A hardware part. Okay, for the first is the ultrasonic sensor for the water level. When there is water arise, the ultrasonic will detect and also close the gate. And for the second sensor, which is a rain sensor, when it detects the heart rate, the sensor will detect and also it will active the gate. And lastly is the water level inside the tunnel. When it detect the water arise, it will close the gate. And also that's all from me.
Assalamualaikum. So after all the hardware has been demonstrated, so all the data that collected from the sensor will be distributed to the cloud. So this is what we are going to do. We are using the InfluxDB and Grafana for the cloud and integration. So this is the interface for the cloud, and this is the bucket, and also the metric for all the distance, which is from the ultrasonic sensor here, the rain sensor here, and the water level sensor here. So if you submit, so this is what we are doing for the past 1 minute. If you want to have an interface for the past 1 hour, so here is the data, and this is the data for the past 30 minutes. 30 days, I'm sorry. So all this data from the InfluxDB then will be distributed to the Grafana. Grafana will collect the data and will indicate to the operator. So this is the dashboard interface for the Grafana. So here the water level sensor, and here the ultrasonic sensor, and here the water level, and here is the dry. So if the ultrasonic sensor is detecting, then we can see it has a real time update. So it will change to yellow color, and if you're too close, it will change to the red color. Yeah, like this. So same goes to the rain sensor. If nothing happens, we'll try. But if there is a rain, it detects rain, then it will goes to the heavy rain, like this. And lastly, for the water level. So it indicates now is 0 unit. If it detects the water, and then it will slowly goes up to 220 units and so on. So that's all for cloud and integration. Thank you very much.
Okay, for demo part, this is the Excel of raw data, and then it is very messy. As you can see here, distance is ultrasonic sensor reading, and then for this one is rain sensor reading, and then this one is the water level sensor reading. So I just convert the raw data Excel into a new Excel. So I put the ultrasonic here, rain sensor here, and water level sensor here, and I insert all of the month from January until December data in the new Excel. And then after got the new Excel, I insert the new Excel into Tableau platform like this. After that, now I will demo how to do a new graph. So I just drag the months to the column because I want the water level by month. I want to see the water level by month. So water level will drag to rows. So now is the sum of the water level. You can change to see the average. And then if you can choose any kind. This one is bar chart. You can choose line chart or area or anything like this. So or you can choose like histogram on the every chart can choose. That's all. Thank you.